Atomic mission and electron configurations. I love fireworks. I always have. There's just something wonderful about watching them explode in the air, all those beautiful colors, and then I know the chemistry behind it, so that makes it even more exciting to me. But what produces all these beautiful colors? And that's what this section of our textbook is really trying to answer. What produces the reds, the purples, the oranges? And that is atomic emission. Atomic emission is the idea that every atom is going to glow a little bit differently when it's put into a flame. So here, lithium, sodium, potassium, calcium, and strontium were all placed onto a tip of a needle and then inserted into the flame. And notice how each one glows a little bit differently. That's why your fireworks glow a little bit differently. They're composed of the different elements, and a good fireworks master will be able to combine them in certain ways in order to release just the colors that they want to see explode in the sky. So, within that, once again, I still haven't answered the question. Yes, they're different, so therefore they're going to glow differently, but why? Why does sodium turn out yellow and strontium's pink? Well, we have these emission line spectrums that you see here. Above it is a continuous spectrum, and that's the light that's produced by the white light. So white light is going to produce a continuous spectrum, whereas emission spectrum, you're going to have discrete. You're going to have specific wavelengths of light that are produced. So looking at sodium or strontium, sodium's got a line right here where yellow is, the energy that's associated with yellow. Whereas strontium has a whole bunch of these reds, but it also has some of these blues, and that's going to be what's producing that more of that pink color. The colors just mixing and combining to it. But then, why does sodium release light at a wavelength that shows up to our eyes as yellow? And that has to do with this nuclear structure of the atom. All that we've been talking about, the Thomson model, developing the plum pudding, all the way to Rutherford's experiments that let us see the nucleus, they built into why elements are the color that they are. So here we see hydrogen and barium's emission spectrum. Hydrogen's very small, barium's a lot bigger, it's a lot more complicated, it's getting a whole lot more lines, but that's not all there is to it. If you think about the nuclear model of an atom, you've got the nucleus in the center and then a whole bunch of electrons are orbiting all around it. And this is the planetary model, the idea that electrons are just going in circles around the nucleus. We now know that electrons don't just go in a circle, they go all over the place. But it's a good model to help us think through. Alright, so let's compare this nuclear planetary model to a ladder. If I were to climb this ladder and I would be on the first rung and I fall off, I'm not really going to hurt myself too bad. But if this is a very tall ladder and I make it all the way to the 6th rung and then I fall off, I'm hurting myself a lot more. And the reason for it is all that potential energy at the top got converted to kinetic energy and makes me go boom there at the bottom. And so I have more energy at the top rung compared to the first rung. It's the same way with the nuclear model. If I'm on that first rung, I don't have as much energy as I would in one of these further models or further energy levels that are further from the nucleus. And the idea for that would be just a simplified version of it. Protons are inside the nucleus, electrons are rotating around the nucleus. Negative and positive charges they want to attract. So in order for that electron to be so far away from the nucleus and still happy and content in its orbit, it has to use a whole lot of energy to be out there. So it has a lot of energy out there. But then if that electron that's really far from the nucleus relaxes down to one of these easier energy levels and starts living the beach life, it's going to release a lot of that energy, and that energy gets released as light. That light is what you see here. Light is in the form of a wave, and that wave has frequency, which is how fast is it moving per minute or per second, and then wavelength is this distance here from crest to crest or from trough to trough. And those are just ways of describing the energy. So these higher energy waveforms down here versus the lower energy. And if it's a far away, if the electron is moving in one of the higher energy levels and it relaxes to the lower one, it's going to produce a lot more energy than as if it was at a lower rung and it fell down to an even lower rung. Not a lot of energy is going to be produced there. And that's what gives you the lights. So these lower energy colors of reds, that might be like an energy level of 2 relaxing to an energy level of 1, whereas the purple, the violet, that might be energy level of 6 relaxing down to a 1. It had a lot more energy to give up, so it gave it as a high energy wave of light. Now, I like to think about this purple and the red. How can I keep track as to which one is more energetic? I like this Foxtrot comic. It's fantastic. So he says, do you sell ultraviolet bowl? Excuse me? What about regular violet bowl? No. Blue bowl? No. Green, yellow, orange? No, no, no. Rats. Okay. I'll take a red bowl. And then he tells his friend, I was hoping for something a little higher energy. And then his friend says, at least it is an infrared bowl. And that being said, it seems like Red Bull is a little misnamed, because if it really was a high energy level, wouldn't it be Blue Bull or ultraviolet? Because that would be pretty funny. But anyway, if that helps you remember that Red Bull is not very energetic and violet is the most energetic color, fantastic. Alright, so now we need to talk about some vocab words. These are things you need to know well. So I've used the word shell a couple of times, and I've also used energy. They're basically the same thing. The shell tells you how far away from the nucleus you are. It also tells you the energy that's associated with that electron. So the lower shells, your 1, your 2, your 3, those are going to be low energy, your 4s, 5s, 6s, etc. The further you are from the nucleus, the more energetic you are. Alright, so then subshells. Subshells are a small part, a subclassification of cells. And all that does is it tells you what shape you are. So you can have a shell of energy 3 with an S or a P or a D. And all that means is I have an energy of 3, but my shape is a circle, or my shape is a dumbbell, or my shape is a flower. So a subshell just tells you your shape. And then orbital is the specific orbital within a subshell that holds 2 electrons. Every orbital can only maximally hold 2. It can hold 1 or 0, but it definitely cannot hold 3. So the S subshell has 1 orbital, which means it can hold 2 electrons, whereas the P subshell has 3 different orbitals, and each orbital holds 2 electrons, which means 3 times 2 gives you 6, and so on. So here is a picture of the shell. So the shell right here is the energy level, like I said. So once again, just keep thinking about it, that the farther you are from the nucleus, the more energy you have. Whereas subshell is shape. Now these are the shapes I was referring to. So you've got a sphere and you've got dumbbells. So these dumbbells right here are just 3 different orbitals, which means you can have 2 electrons in the yellow, 2 in the green, and 2 in the blue, giving you a total of 6 electrons in the P subshell. Now, the size of these orbitals just grows. So think about the circle getting bigger and bigger. But within that sphere, so it's electron density. Those electrons aren't just going around the edge of it. They're going all inside of it in the full volume that is that s orbital. They're moving around like crazy. So if you have an n equals 1s, it's small, but then an n equals 2s is bigger, so it'll actually overlap with the s equals the n equal 1s orbital. And same thing for the p orbitals. Alright, so now we need to figure out where do we need to put these electrons. And figuring out where these electrons go is in, do they go in the 1, the 2, the 3, do they go in the S, the P, the D? That is part of what's called electron configurations. And what you see here is just ways of writing the electron configurations. So first off, you tell it what is the energy level. So this 1 is telling you which energy level is it in. Okay, so these are in the first shell. Then S tells you what subshell you're in. Is it S, P, or D? And then the superscript here tells you how many electrons are in that specific subshell. Okay, and this subshell is the 1s subshell. So let's do some examples. It'll make more sense as we go. But first off, your subshells have different energy. So remember how I said the 1s has more energy than the 2, than the 3, than the 4, because the 4 is further from the nucleus, so it's going to have more energy. This is the Aufbau principle, and it tells you what order to fill them in. So you fill things, if you have 1 electron, it's first going to try and enter 1s, then 2s, then 2p, then 3s, then 3p, and so on and so forth. And why for that is just your people, just like electrons, are lazy. You try and do the lowest energy thing first, and then you can go to the higher energy level things. This is a systematic way of doing it. So if you want to think about it as you fill these boxes in this order, you can print this off and you can practice using this, and I find this to be pretty helpful. Put electrons here, then here, then here, and they actually do fill in that way, where you fill in 1, 1, 1, and then come back 2, 2, 2. And then you'd fill here, and then 1, 1, 1, 2, 2, 2, and then 1, 1, and then 1, 1, 1, 1, 1. So you actually do fill them in that order. Alright. So then this chart in your textbook kind of tells you the handy-dandy way of visually figuring out where electrons are going to be. So meaning this element right here has electrons in the 1s, the 2s, the 2p, and then the 3s as well. An electron here has everything above it, the 4s, the 3d, with the 3d being the subshell that houses the last electron. So this, I think, once you practice a little bit, will be a very useful diagram. And then this is just a simple way of saying whenever you're writing these electron configurations, it lets you see what's called valence electrons readily. So your core electrons are the central electrons. These valence electrons are going to be electrons that are utilized in bonding. And so as we go throughout the course of this class, these valence electrons are going to be pivotal and very important. So being able to look at a periodic table and quickly be able to say it has 4 electrons, valence electrons, it has 6 valence electrons. That is going to be something that we're going to use quite often. So let's practice. This is how I learned, and just practice, practice, practice. The more you practice, the better you're going to get at it, and you'll find you can pretty much pick any element and just practice it and then type into Google electron configuration for blah, and then you'll be able to check your work and see if you did it right. So we're going to do the electron configuration for oxygen. So oxygen is located right there, which means it is in column 6A, it is in row 2. And it also has 8 electrons. So if we look at everything before it, which means it has some electrons in 1s, some in 2s, and then some in 2p. And so now all we have is 8 electrons. Let's put them into these boxes and see what happens. As we do it, we are going to fill the 1s first. Then we're going to fill the 2s up, then down, and every arrow represents 1 electron. So we have 8 of these arrows to fill. So next we're going to fill in the 2p like this first, and then we're going to come back with our last electron and fill in the first box of 2p. This is just convention, but the idea would be if you have an option of a dorm room that you're a single person in there, so you're all by yourself in the dorm, or you have to have a dorm mate, you're probably, and you're told it's the same price, same cost, you're probably going to choose to have your own room. And that's the same thing for electrons. They want their own room first before they're forced to have a roommate. Alright, so then how we write this is 1s2, because there's 2 electrons in the 1s, there's 2 electrons in 2s, and then there are 4 electrons in the 2p, and you write it like this. Alright, let's try again. So now magnesium. Magnesium is located in column 2A, row 3. This means magnesium has electrons in the 1s, the 2s, the 2p, and the 3s orbitals. So I just went with everything that was on this chart before it. And then magnesium has 12 electrons. Remember, now how did I know magnesium has 12 electrons? Remember, you look at the element, and then you look at the number above it, and that number is going to tell you it has 12. It has an atomic number of 12. So now I need to put those 12 electrons into my boxes. So I fill my 1s first, then my 2s, then all my up arrows for 2p, then all my down arrows, then my 3s, and it's filled. That is my orbital configuration, and this is my electron configuration. So you can see you have 1s2, 2s2, 2p6, and 3s2. Alright, do this one on your own. So then you fill in all your arrows, and that is your orbital diagram, and then you write down your electron configuration. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, and 4p6. Now sometimes you'll see it rearranged where you put all your 1s together, then all your 2s, then your 3s, then your 4s, and I don't think our textbook cares. Alright, so now, a little bit of names. Columns are called families or groups, and the reason for that is they share similarities, just like families might share similarities. You know, like even the Brady Bunch, even though they're a blended family, they share a common attributes, that of a common home, a common address, that kind of thing. So we've got these different names for the families. So the alkali metals, the alkaline earth metals, the intertransition metals, the transition metals, and the halogens and noble gases. So these are just families or names to become familiar with. The horizontal rows are called periods. These trends are called periods because they're cyclic, so meaning you might have an increase in a property and then you go down a row and then it's an increase in that property again. So they're more periodic or cyclic in their properties rather than shared. Alright, so then the last trend to look at is that of metals, nonmetals, and noble gases. And so you can see it on the periodic table quite readily, where the nonmetals and the metals are separated here by this dark black line. Okay, and then here you see your noble gases. Alright, go complete all your homework for Chapter 3.